A thin ribbon could one day stretch from Earth to the stars. This is the vision of the Mega Space Elevator, a structure designed to make space travel as simple as riding a lift. If rockets are the daredevil mountain climbers of space access, then space elevators are the steady, reliable cable cars, promising a gentle and reusable journey to orbit. By the end of this exploration, you will understand the incredible engineering feats required to build this cosmic bridge and how it could forever change our relationship with the final frontier. We will confront the search for a material strong enough to form a cable thousands of kilometers long and the violent forces it must survive in our upper atmosphere. What single challenge do you believe will be the most difficult to overcome? That slender ribbon is more than just a cable. It is a carefully balanced system, a cosmic dance between Earth's gravity and the outward pull of a spinning orbit. At the heart of this design is the counterweight, a mass stationed far beyond geostationary orbit. Think of it like swinging a ball on a string around your head. The ball wants to fly away, and that tension keeps the string taut. In our space elevator, that outward force perfectly counters the immense gravitational pull on the long tether below, preventing the entire structure from collapsing back to Earth. This creates a stable, permanent bridge. The base of this bridge would likely be a massive sea platform, offering mobility to dodge storms and ships, anchoring our gateway to the stars in the vast, open ocean. From this base, robotic climbers, powered by lasers or microwaves from the ground, would begin their slow, steady ascent. They would not race skyward in a violent burst of flame. Instead, they would glide upwards for days, carrying their payloads in a smooth, controlled ride. This is the revolutionary promise. The cost of launching anything into space could plummet from tens of thousands of dollars per kilogram to just a few hundred, or even less. It transforms access to orbit from a rare, expensive event into a routine, almost mundane operation. This is the vision that has captivated thinkers for over a century, from the early dreams of Konstantin Tsiolkovsky to the vivid stories of Arthur C. Clarke. Modern pioneers like Dr. Bradley Edwards have worked to translate this science fiction into a tangible engineering blueprint, arguing that the fundamental physics are sound. So if the concept is so elegant and the payoff so immense, what is stopping us from building it tomorrow? The answer lies in a single, monumental challenge, a problem that brings us back to that delicate-looking ribbon. We must find or create a material with strength beyond anything we currently possess. This perfect tether must be a material that defies our current reality. It needs a specific strength, a measure of its toughness relative to its weight that is utterly unmatched. To visualize this, picture a single strand, thinner than a human hair, yet strong enough to hoist a family car. Now imagine that strand stretching tens of thousands of kilometers into the sky, supporting not only its own immense weight, but also the dynamic stresses of climbers and the harsh environment of space. Conventional steel would snap under a fraction of this load. This is the monumental challenge that brings two wonder materials to the forefront: carbon nanotubes and graphene. These are not metals or plastics, but structures built from lattices of carbon atoms, arranged in a perfect hexagonal pattern. On a theoretical level, the bonds between these atoms are so strong that a cable made from them could possess the necessary strength to make the elevator possible. The origins of this research trace back to the late 20th century, with scientists discovering how to create and manipulate these nanomaterials. Yet, the leap from a microscopic sample in a lab to a continuous cable thousands of kilometers long is staggering. Materials scientist Ray Bauman has highlighted that manufacturing flawless, macro-scale nanotubes is akin to weaving a thread from individual molecules. It is a delicate and precise art where a single atomic defect, a misplaced row in the molecular lattice, could become a point of catastrophic failure under the immense tension. This forces engineers to think beyond a single material. The tether would likely be a complex composite, a blend of different nanostructures. For example, boron nitride nanotubes could be woven in to provide resistance against the intense radiation in the upper atmosphere, while theoretical diamond nanothreads might offer unparalleled durability. This design must also incorporate redundancy, with countless nanoscale fibers working in unison, so that if one fails, the load is instantly transferred to its neighbors. Some concepts even include self-healing capabilities, where embedded microcapsules of adhesive could seal minor punctures from micrometeorites. How do you design for such perfection across such a vast distance, where you cannot send a repair crew? Every meter of this cosmic ribbon must be engineered to survive a gauntlet of forces, from the relentless gravitational pull at its base to the whipping centrifugal force at its top. Solving this material puzzle is a monumental step, but it only brings us to the next great challenge: securing our foothold here on Earth. Securing our foothold on Earth means confronting a planet that is far from a tranquil host. The base of the space elevator must endure an onslaught of terrestrial fury. Picture a structure rooted in the open ocean, lashed by hurricane-force winds that could shred steel. It becomes the tallest lightning rod in human history, attracting strikes of unimaginable power, while corrosive salt spray works tirelessly to weaken its every component. This is not a static monument. It is a living system that must adapt and respond. Our solutions draw from historical engineering triumphs. Deep-sea oil rigs withstand monstrous waves, and modern skyscrapers sway gracefully in high winds. Yet this project combines and magnifies those challenges on an unprecedented scale. The tether itself acts like a colossal sail, catching the wind across its entire length and threatening to whip the entire structure into destructive oscillations. To counter this, aerospace experts like Dr. Anita Sengup to propose dynamic stabilization. Imagine a network of thrusters and active dampers, constantly making tiny corrections. These systems would act like a surfer, constantly shifting their weight on a massive wave, using real-time data to neutralize the push of the wind and the rhythmic pull of ascending climbers. The tether's surface would need advanced coatings to prevent ice from accumulating in the upper atmosphere, a heavy, uneven load that could unbalance the entire system. And for the robotic climbers inching their way upward, redundant power systems are essential. If the primary ground-based laser is obscured by a storm, a backup must take over instantly, preventing a climber from stalling mid-journey. Emergency protocols would be as critical as the structure itself. In the face of a Category 5 cyclone, the system might need to execute a rapid retraction of the lower tether section, pulling it above the worst of the weather, or initiate a coordinated evacuation of all climbers to safe stations. This is about building resilience into every single component. How would you design a system to remain operational when nature unleashes its full power? Conquering this atmospheric gauntlet is a monumental achievement, but it merely stabilizes the anchor point for an even greater challenge. The true test of the tether's design begins as we follow its path upward, through a gauntlet of orbital traffic and cosmic debris that threatens its very existence. That slender ribbon, now secured against Earth storms, must now hold its own against the silent music of the cosmos. It behaves like a colossal guitar string, one plucked by the gravity of the moon, the pressure of solar wind, and the very spin of our planet. These are not sudden impacts, but persistent nudges that can, over time, build into destructive, whip-cracking resonances. The core principle, first detailed by Yuri Artsutanov, is a delicate equilibrium. Earth's gravity pulls down while the counterweight's centrifugal force pulls outward, creating a tense, stable cable. Yet this balance is perpetually disturbed. Orbital dynamicists like Dr. John Pearson highlight a less obvious force, the Coriolis effect. As Earth rotates beneath the stationary tether, it induces a gentle, pendulum-like sway, a constant back and forth motion that must be actively managed. This dynamic system is further complicated by its own traffic. Each robotic climber, inching its way upward, transfers momentum to the tether. A climber ascending acts like an ant crawling up a suspended rope, causing the entire line to sway. If multiple climbers move without coordination, their tiny pushes could combine into a powerful, traveling wave. Preventing this requires predictive algorithms of incredible sophistication, scheduling each climber's journey not for speed, but for stability, their movements choreographed to cancel out oscillations rather than amplify them. The system must also guard against harmonic frequencies. If the tether's natural vibration happens to match the rhythmic tug of Earth's orbital periods, energy would build up continuously, like a singer shattering a glass with the right note. Lessons from history underscore the severity of this challenge. The Tethered Satellite System missions, a joint project by NASA and the European Space Agency, involved a satellite deployed on a cable just a few dozen kilometers long. Even at that tiny scale, the tether exhibited unexpected and complex motions, proving how difficult it is to control a flexible structure in space. Scaling this up to a tether 100 times longer magnifies the problem exponentially. The solution lies in a nervous system woven into the ribbon itself. A network of distributed sensors would monitor strain and motion, while small, efficient thrusters spaced along the length would provide gentle, real-time corrections. This is where artificial intelligence becomes the silent conductor. An AI-driven control system could learn the tether's unique rhythms, anticipating a dangerous oscillation before it even begins and issuing commands to neutralize it. How do you teach a machine to feel the music of the spheres and play a counter-melody to keep the peace? Taming these invisible forces is a monumental task in control theory, but it grants us passage through the final protective layer of our atmosphere, only to arrive at the most cluttered and dangerous frontier of all, low Earth orbit. Rising above the atmospheric turbulence, the tether now enters the most crowded neighborhood in space. Low Earth orbit is a celestial junkyard, filled with the silent, speeding remnants of our own ambition. Defunct satellites, spent rocket stages, and countless fragments, some no larger than a paint flake, zip around the planet at speeds exceeding 10 kilometers per second. At these hypervelocities, a single millimeter-wide particle does not just hit the tether. It delivers an explosive kinetic punch capable of severing a critical cable. This is the ultimate paradox of progress. The very infrastructure we built to explore the heavens could become the shrapnel that destroys our most ambitious bridge to them. Experts at the European Space Agency's Space Debris Office have long warned that this growing cloud of debris requires active management, not just passive hope. For a structure as vast and permanent as a space elevator, simply hoping to avoid a hit is not a strategy. It is a recipe for disaster. So how do we armor a ribbon tens of thousands of kilometers long against an invisible hailstorm? The solution is a layered defense, combining ancient principles of redundancy with futuristic active protection. The tether itself would not be a single, vulnerable strand. It would be a complex braid of thousands of individual nanofibers. If a debris particle slices through one section, the surrounding fibers would instantly redistribute the immense load, isolating the damage like a fused circuit in your home. This built-in redundancy is the first and most crucial layer of survival, but we cannot rely on armor alone. The second layer is awareness. The elevator would need its own sensory nervous system, a network of radar and LiDAR units scanning constantly for incoming threats. This data would feed into a global space traffic management system, coordinating with satellite operators to predict potential collisions hours or even days in advance. When a dangerous object is identified on an intercept course, the entire elevator might execute a gentle, coordinated maneuver. By using small thrusters along its length, it could sway the tether just enough to let the debris pass harmlessly by, a delicate dance to avoid a catastrophic embrace. For the smallest, untrackable debris, more radical concepts emerge. Laser arrays mounted on the counterweight or at intervals along the tether could focus beams of energy to vaporize tiny particles just before they strike. Other proposals suggest deploying sacrificial nets or aerogel shields that could capture larger fragments, safely clearing a path. This constant, vigilant defense highlights a profound responsibility. Every new satellite we launch, every piece of hardware we leave in orbit, adds to the challenge of keeping this cosmic pathway safe. How do we expand our presence in space without polluting the very routes we hope to travel? Successfully navigating this orbital debris field is a monumental achievement in itself, but it only grants passage into a far more hostile and silent realm, where an invisible and relentless form of energy awaits. Beyond the protective shroud of our lower atmosphere, the elevator's path carves directly through one of Earth's most formidable natural barriers. The Van Allen radiation belts are vast, donut-shaped zones of intense radiation, holding trapped protons and electrons captive within our planet's magnetic field. Discovered in 1958 by scientist James Van Allen, these belts present a gauntlet that every climber must pass through slowly and deliberately. For days or even weeks, both delicate electronics and any human passengers would be bathed in this invisible, energetic storm. Radiation health experts like Dr. Kerry Lee emphasized that the key challenge is not just blocking this radiation, but doing so without making the climbers impossibly heavy. You cannot simply wrap the entire vehicle in thick lead. The solution lies in smart materials. Hydrogen-rich substances like certain plastics or polyethylene are remarkably effective at scattering incoming particles without the crushing weight of metal. The International Space Station already uses modules where water stores double as protective walls, a clever dual-purpose approach that could be vital for the climbers. But the space station orbits below the most intense regions. Our elevator is a permanent fixture within them, a stationary target for a continuous barrage. This demands a new level of ingenuity. Some concepts propose active magnetic shielding, creating a miniature, localized magnetic field around the climber to gently deflect charged particles away, much like Earth's own magnetosphere does on a planetary scale. Yet, even with the best passive and active shields, a sudden solar flare could unleash a torrent of radiation that threatens to overwhelm the system. In such an emergency, the climber would need a dedicated storm shelter, a small, heavily shielded core where passengers could wait out the event, surrounded by the vehicle's own water and food supplies. The electronics themselves would need to be radiation-hardened, designed with redundant circuits that can tolerate occasional glitches and keep functioning. How do you build a computer that can think straight while being bombarded with atomic shrapnel? Solving this puzzle of prolonged exposure is a quiet, relentless battle for reliability. With the climbers protected from this invisible rain, we can finally turn our gaze to the far end of the tether, where the final piece of this cosmic balancing act holds everything together. That final anchor point far out in the void is the masterstroke of the entire design. It is a counterweight, a mass station tens of thousands of kilometers beyond geostationary orbit, pulling the entire tether taut with the raw force of its own momentum. Think of it as the ball at the end of a cosmic string you are swinging around your head. Without that outward pull, the string would simply fall back to you. Here, the counterweight's centrifugal force perfectly balances Earth's relentless gravity, creating a stable, stationary bridge to the stars. This is not just a passive mass. It is the keystone of the entire structure. Orbital engineers like Dr. Paul Birch envisioned it as a bustling hub, a destination in its own right. Its required mass is staggering, calculated to offset not only the immense weight of the tether itself, but also the constant strain of robotic climbers crawling up and down its length. So where do we find such an anchor? One concept involves the ultimate form of cosmic recycling, capturing a small, near-Earth asteroid and nudging it into the perfect position. Another proposes building a massive, manufactured station from scratch, perhaps constructed from materials mined on the Moon. This station could be equipped with expansive docking ports, becoming a gateway for spacecraft arriving from deeper space or departing for the outer solar system. The principle relies on a specific altitude, 35,786 kilometers up, where an object's orbital period matches Earth's rotation. At this geostationary point, the elevator appears to hang motionless in the sky, a fixed celestial landmark, but this balance is dynamic, not static. Every time a climber ascends, it transfers a tiny amount of momentum to the tether, creating a slight shift that the system must constantly correct. The counterweight must be designed to handle these rhythmic tugs, its mass and position finely tuned to absorb the energy without setting the entire ribbon into a dangerous sway. This transforms the counterweight from a mere weight into a multi-functional asset. It could host vast arrays of solar panels, beaming clean energy directly to Earth via focused microwaves. It could serve as the ultimate communications relay, a node connecting every corner of our planet with unparalleled clarity. How might we make this distant outpost self-sustaining? It could process raw materials from captured asteroids, manufacturing fuel and spare parts for itself and passing ships, turning a structural necessity into the first true industrial park in deep space. With this cosmic anchor holding our bridge firmly in place, our attention shifts to the vehicles that will bring it to life, the robotic climbers designed to traverse this impossible thread. These robotic climbers are the true workhorses of the system, transforming the static tether into a dynamic highway. Their design is a masterpiece of compromise, balancing the need to be feather light against the demand to be unshakably strong. Picture a vehicle no larger than a shipping container, gripping the ribbon with sets of motorized traction wheels. It does not roar into the sky on a pillar of fire. Instead, it begins a silent, steady ascent that could last for days, powered not by internal fuel but by energy beamed from the planet below. This is the core innovation. By leaving the heavy power generation on the ground, the climber can dedicate more of its mass to its precious cargo, whether that is a delicate communication satellite, a modular component for a space station, or a pressurized capsule for human pioneers. Early concepts from groups like NASA Advanced Concepts Office explored everything from tank-like treads to magnetic levitation systems, all seeking the perfect balance of grip and efficiency. The propulsion mechanism itself is a quiet marvel of engineering. Electric motors drive arrays of wheels that clamp gently onto the tether, their pressure carefully calibrated to provide enough friction for the climb without damaging the delicate nanoribbon. Some designs propose a linear induction system, where the climber acts as the rotor of a motor and the tether itself becomes the stator, creating a contactless magnetic push skyward. This journey is not a uniform experience. As the climber rises, the forces acting upon it subtly shift. The crushing grip of gravity weakens slightly, while the outward tug of centrifugal force grows stronger. This results in a gradual, perceptible change in apparent gravity for anything inside the climber. A 100-kilogram payload would feel a tiny bit lighter with every passing hour, a constant reminder of the cosmic balancing act in which the vehicle is a participant. Managing this environment requires sophisticated thermal control. In the vacuum of space, there is no air to carry away heat, so the climber must use intricate systems of radiators and heat pipes to dissipate the warmth generated by its motors and electronics, all while ensuring its cargo stays within a strict temperature range. Safety is engineered into every decision. Redundant, independent braking systems are non-negotiable, capable of halting the climber's ascent instantly should any anomaly be detected. Its navigation must be fully autonomous, using a network of sensors to maintain a safe distance from other climbers on the same tether, orchestrating a slow-motion celestial ballet to prevent mid-air traffic jams tens of thousands of kilometers up. One of the most promising innovations involves superconductors. If the climber can be cooled to extremely low temperatures, it could use superconducting magnets to levitate just above the tether, eliminating physical contact and friction entirely. This would dramatically reduce wear on the ribbon and slash the energy required for the long climb, but this raises a pivotal question. What new forms of energy storage or transfer could make these climbers even more capable? Engineers are exploring ultracapacitors that can release power in quick bursts for acceleration, or perfecting the efficiency of wireless power transfer from ground-based lasers to keep the climbers moving reliably through Earth's atmosphere. The perfection of this mechanical spider, inching its way to the stars, is a triumph in itself, yet it forces us to confront the staggering appetite for energy that the entire system would demand. The sheer scale of energy required is almost beyond comprehension. To push a climber and its payload against Earth's gravity for days on end demands a constant, colossal stream of power, measured in hundreds of kilowatts for even a modest vehicle. The traditional solution of carrying fuel is a non-starter. The weight of the propellant and engines would quickly overwhelm the climber, making the entire ascent self-defeating. This fundamental dilemma forces a radical rethink of energy delivery, moving the power source off the vehicle entirely. The most promising concept involves beaming that power directly to the climber from the ground. Imagine a network of ground-based transmitters, likely powerful lasers or microwave arrays, focusing their energy onto a receiver, a retina on the climber's underside. This is not a simple spotlight. Energy experts like Dr. James Benford advocate for phased array transmitters, which can electronically steer their beam with incredible precision, tracking the climber as it rises through the sky without any moving parts. This technology ensures the energy is delivered efficiently over the vast and growing distance, but the atmosphere itself is a fickle medium. Clouds, rain, and even turbulent air can scatter and absorb the beam, leading to significant power loss. This requires sophisticated adaptive optics, systems that can subtly deform the transmitter's mirrors in real time to compensate for atmospheric distortion, keeping the energy tightly focused on its target. The safety implications are profound. How do you operate a gigawatt-scale energy beam without it becoming a hazard to aircraft or satellites? The answer lies in multiple, redundant safety systems. The beam's frequency could be chosen to be harmless to most materials, and the transmission sites would be located in strict no-fly zones, likely far out at sea. The system would be designed with automatic shutdown protocols, able to detect any unintended object entering the beam path and cutting power in a fraction of a second. For the climber, the engineering challenge is converting this beamed energy into reliable motion. The rectenna, a vast, lightweight grid on the climber's belly, would capture the incoming waves and convert them directly into electricity to drive the traction motors. Some designs even propose a form of regenerative braking for the descent. A climber returning to Earth, laden with valuable resources from an asteroid mine, could use its motors as generators, slowing its fall while producing a surge of electricity that could be beamed back to the ground or stored for other climbers. But ground-based power is only part of the equation. The counterweight station itself, that distant anchor, has its own massive energy needs for station keeping, communications, and any manufacturing it performs. Here, the vacuum of space offers a perfect environment for massive solar arrays, unfurling to capture uninterrupted sunlight. For consistent, high-output power regardless of the sun's position, more advanced concepts enter the discussion, such as compact nuclear reactors, which could provide a steady, reliable source of energy for decades. This intricate power web, spanning from the Earth's surface to the edge of space, highlights a pivotal transition. It moves us from treating energy as a commodity we burn to a utility we manage and beam across the solar system. How do we regulate such a powerful network to ensure it serves all of humanity? This question of governance becomes the final, and perhaps most human, challenge for our cosmic bridge. This cosmic highway cannot exist in isolation. It must merge seamlessly with the bustling traffic of our existing orbital infrastructure, becoming a new nexus in a sky already filled with satellites, space stations, and the occasional launch vehicle. The integration is a monumental exercise in logistics and diplomacy, requiring a global system of coordination never before attempted. Imagine an air traffic control network, but one that operates on a planetary scale, managing objects moving at orbital velocities across tens of thousands of kilometers. This system would need to harmonize the slow, steady ascent of climbers with the swift, predictable paths of satellites, ensuring a safe distance is always maintained. The foundational law for all this activity is the Outer Space Treaty of 1967, which establishes space as a province for all humanity. Yet, as space lawyer Dr. Franz von der Dunk points out, this treaty was drafted long before a structure like a space elevator was conceivable. It provides a vital legal framework, but the specific regulations for elevator corridors, right-of-way, and liability are entirely undeveloped. This legal vacuum prompts an urgent call for new international agreements, treaties that would define the elevator's protected operational zone and establish clear protocols for every participant. Technically, every climber would need to be as visible as a commercial airliner. This means implementing robust transponder systems that broadcast its precise position, velocity, and status to every satellite and agency in near real time. A centralized traffic management authority would use this data to choreograph the celestial dance, issuing navigational corrections to avoid potential conflicts days in advance. But what happens when the choreography fails? Consider a scenario where a climber suffers a catastrophic malfunction, loses power, and begins to drift silently into the path of a multi-billion-dollar communications satellite. The immediate question is one of liability. Who is responsible for the damage, and how do we safely recover or deorbit the stricken vehicle before it causes a chain reaction of collisions? The answers require pre-established international emergency response teams and fail-safe abort procedures. A climber might be programmed to automatically detach and use a small, independent propulsion system to move itself into a safe, graveyard orbit if its primary systems fail. The challenge of integration is starkly illustrated by the geostationary belt itself, the very orbit where the elevator is anchored. The slots for satellites in this precious orbital real estate are already fiercely contested and allocated by international bodies. Adding a permanent, massive structure like a space elevator would necessitate reserved slots and new definitions of what it means to occupy an orbital position. How do we fairly allocate access to this new gateway to the stars, ensuring it serves all nations and not just a privileged few? Successfully weaving this single thread into the fabric of our orbital activities sets the stage for the most pragmatic question of all: the economic forces that would ultimately determine if this bridge can be built. The financial scale of this project is almost beyond earthly comprehension. We are no longer discussing the budget for a single mission, but the capital required to build a new, permanent piece of our planet's infrastructure. Funding a mega space elevator demands a paradigm shift in economic thinking, moving from the short-term cycles of rocket launches to a multi-generational investment horizon. The most plausible model is a global public-private partnership, pooling resources from nations and corporations to cover a price tag estimated in the trillions of dollars. This is not an expense but a foundational investment, amortized over centuries, much like the great cathedrals of old or the interstate highway systems of the modern era. Financial analyst Dr. Alan Wasser points to historical precedents like the Panama Canal or the International Space Station, where the immense upfront costs were justified by the long-term strategic benefits and the creation of entirely new economic ecosystems. The ultimate payoff is a dramatic reduction in the cost to reach orbit. Early studies by the International Academy of Astronautics suggest that once operational, the elevator could eventually bring prices down to below $100 per kilogram, a figure that would shatter every economic barrier to space. The revenue streams to pay back this colossal investment are as diverse as they are revolutionary. The most straightforward is payload launch, charging for the gentle ride to orbit for satellites, space station modules, and fuel depots. But the business model extends far beyond simple freight. Tourism offers a premium tier, with climbers featuring panoramic windows for those willing to pay for the life-changing vista of Earth from the heavens. The tether itself becomes valuable real estate, with companies leasing space to mount telescopes, climate sensors, and other scientific instruments at altitudes impossible to maintain with free-flying satellites. Perhaps the most transformative opportunity lies in supplying the next great industry, asteroid mining. The elevator would be the perfect conduit to send heavy mining equipment and processing factories into space, and then to bring the harvested precious metals and water back to Earth or to orbiting depots. One of the most compelling visions involves space-based solar power. A single elevator could provide the cheap, routine access needed to construct vast solar arrays in geostationary orbit, which would beam clean, continuous energy to the planet, generating a perpetual revenue stream. This raises a fascinating question for our era. How might we democratize such a monumental project? Could crowdfunding campaigns or blockchain-based token investments allow ordinary people to own a small piece of this cosmic bridge, spreading the financial risk while building global public support? Establishing this financial viability is a monumental achievement in spreadsheet diplomacy, but it is a hollow victory if we cannot guarantee the safety of the people who will build and ultimately ride this incredible structure. This forces us to confront the final, deeply human challenge, the practical reality of its construction. Building this cosmic thread will be a marathon, not a sprint. Its assembly broken into a deliberate sequence of stages to manage unprecedented risk. The first phase begins not with a climber, but with a rocket launching a slender seed tether and a modest counterweight into the perfect geostationary position. This initial strand is not yet strong enough to support a full ascent, but it serves as the foundational cord, the very first line cast into the celestial ocean. From this point, the construction becomes self-reinforcing. Specialized robotic climbers launched from Earth will latch onto this initial ribbon. Their mission is not to carry cargo, but to crawl upwards, meticulously weaving additional nanotubes into the structure, layer by layer, strengthening the tether with each successive trip. This iterative process, echoing the patient work of a spider spinning its web, gradually builds the ribbon from a fragile thread into an unbreakable cable capable of supporting its own immense weight and the climbers to come. This phased methodology draws directly from monumental terrestrial projects like the Channel Tunnel, where individual sections were assembled and tested separately before their historic connection beneath the sea. Proposals from groups like Liftport Group outline a realistic, if ambitious, timeline stretching over 20 years, a testament to the methodical patience required. The entire operation would be managed by construction managers like Dr. Michael Lane, who emphasized that almost all assembly will be performed by advanced robotics in the harsh environment of space. These machines would work from temporary staging platforms anchored at critical altitudes, using materials either launched from Earth or, in later stages, harvested from nearby asteroids to drastically reduce the immense logistical cost. Throughout this decades-long process, a distributed network of sensors embedded within the tether itself would perform continuous quality control, monitoring for microscopic stresses or manufacturing flaws in real time. Contingency plans are as vital as the primary blueprint, with specialized repair climbers on standby to swiftly patch any section damaged by micrometeorites or material fatigue during the delicate build-out. But such a long-term project raises a compelling question. Could this partially built elevator offer interim benefits to help fund its own creation? Even a half-finished tether, reaching only partway to orbit, could host high-altitude research platforms for atmospheric science, serve as a unique communications relay, or provide a testing ground for new materials and technologies, generating early revenue and invaluable data. With the structure steadily rising, our focus must shift from the machines that build it to the people who will ultimately live and work within this soaring city in the sky. The human element is the final and most vital component in this grand equation. A diverse crew of specialists from pilots to life support technicians would need training that merges the disciplines of astronaut, sailor, and high-rise engineer. Their environment is a vertical city under tension, a realm of shifting forces and profound isolation. The journey itself is a unique psychological trial. Unlike a rocket's brief, intense ride, the climber's ascent is a slow, deliberate process where Earth gradually recedes over several days. This prolonged confinement in a narrow, vertical shaft presents a mental challenge unlike any other, demanding resilience and specialized psychological support to combat the sensation of being suspended in an endless climb. Human factors experts like Dr. Patricia Sanders apply lessons from decades aboard the International Space Station, designing habitats that manage both the body and the mind. The crew must be prepared for the subtle change in apparent gravity, from Earth normal at the base to weightlessness at the top, and everything in between. This requires physical training regimens and operational procedures that adapt to a continuously variable environment, but training for normal operations is only half the battle. Emergency protocols must be as robust as the tether itself. In the event of a catastrophic failure, such as a climber losing power or a critical system failing, the response must be swift and sure. Evacuation plans could involve detachable crew modules, self-contained units equipped with their own propulsion and re-entry systems. These modules could separate from the stricken climber and execute a controlled descent, using inflatable heat shields to survive the fiery passage through the atmosphere. For emergencies higher up the tether, a network of safe haven stations could be spaced along the ribbon, pressurized outposts where crews could await rescue in a stable environment with independent life support. Detailed safety systems are woven into every aspect of the design. Redundant life support systems ensure a constant supply of air and water, while dedicated radiation shelters within the climber provide protection against unpredictable solar storms. Regular, immersive drills would be mandatory, simulating scenarios from fire and decompression to a complete power loss, ensuring every crew member's actions become instinct. How do you practice escaping a vehicle that is simultaneously a building, a train, and a spacecraft? The answer lies in massive simulators that recreate the sights, sounds, and stresses of the real environment, building muscle memory for the most demanding situations. This relentless focus on human readiness is inseparable from the physical structure they inhabit. The elevator's integrity is not a static condition, but a state of constant preservation, demanding a perpetual cycle of inspection and repair to safeguard the lives that depend upon it. This cosmic bridge is not a monument we build and forget. It is a living entity demanding a perpetual, silent conversation with the forces that seek to erode it. A dedicated fleet of robotic sentinels would crawl the tether endlessly, their optical sensors and laser scanners hunting for microscopic fatigue, the faintest scar from a debris impact, or the subtle wear on a traction guide. Their mission is preservation, extending the elevator's operational life beyond a full century. This maintenance philosophy is borrowed from the most demanding fields on Earth. Like the non-destructive testing used on aircraft wings and suspension bridges, these inspectors use ultrasound and magnetic resonance to see inside the tether's composite layers, predicting a failure long before it happens. Reliability experts like Dr. Nancy Curry envision distributed robotics, small repair climbers that live on the tether itself. They would respond to alerts, scuttling to a damage site to perform autonomous surgery. Using onboard 3D printers fed by raw material from depots at the anchor stations, they could fabricate and fuse a perfect patch over a micrometeorite puncture, a process taking hours instead of weeks. The most advanced concepts involve self-healing materials. Imagine the tether's core being laced with countless microscopic capsules of a liquid adhesive. If a particle tears through the structure, these capsules would rupture at the point of impact, releasing their glue to seamlessly fill the void and restore strength. Key tasks for this perpetual upkeep are as varied as the threats themselves. They range from the physical, like reapplying specialized lubricants to the climber's traction mechanisms, to the digital, with constant wireless software updates for the complex AI control systems that manage the tether's stability. An overarching artificial intelligence would schedule all this work, modeling material degradation from relentless ultraviolet radiation, atomic oxygen erosion, and the constant cyclical stress. It would know a component is nearing its end of life long before a human operator might notice a problem. This system finds a real-world parallel in the ongoing, intricate upkeep of the International Space Station, but scaled to a structure 100 times longer and exposed to far more extreme conditions. How would this network respond to a crisis during a solar maximum, when radiation levels spike and threaten both the robots and the tether's electronics? The entire regime would need hardened redundancy, with shielded maintenance climbers prepositioned to handle critical repairs even during a proton storm. This relentless focus on preservation underscores a simple truth. The elevator's greatest challenge may not be its construction, but its perpetual care, a commitment stretching across generations. This physical upkeep, however, is only one dimension of its protection. A structure of such immense strategic value must also be defended against a more deliberate form of threat. A structure of this magnitude and importance would inevitably become a symbol, and with that status comes a profound responsibility to protect it. The same qualities that make the space elevator a revolutionary gateway, its permanence and accessibility, also render it a potential target for those wishing to cause disruption on a global scale. This is not merely about protecting a piece of infrastructure, but about safeguarding a new artery for human civilization. The security strategy must be as multi-layered as the tether itself, operating from the deep ocean to the vacuum of space. At the most fundamental level, the digital nervous system of the elevator requires absolute protection. Every climber, every thruster, and every sensor is a node in a vast network, and a sophisticated cyber attack could be as devastating as a physical one. Security protocols would employ unbreakable quantum encrypted communications for all command and control signals, creating a secure channel that cannot be intercepted or mimicked. Physical access at the base station would be governed by biometric scans and behavioral analysis, ensuring that only authorized personnel can enter critical control centers. This fortress-like approach extends to the surrounding environment. The mobile ocean platform is not just for weather avoidance, it is a core security feature, constantly drifting to present a moving, unpredictable target. A fleet of autonomous patrol drones, both on the surface and in the air, would maintain a wide perimeter, their advanced sensors calibrated to detect and identify any unauthorized vessel or aircraft long before it becomes a threat. For more direct dangers, such as a missile launch, the system would integrate with global defense networks, potentially employing directed energy weapons to neutralize incoming projectiles. Security expert Dr. John Pike emphasizes that no single nation can bear this burden alone. The protection of the elevator would likely necessitate an unprecedented level of international cooperation, perhaps leading to the formation of a dedicated Space Guard force operating under a United Nations mandate. This force would be responsible for monitoring the entire length of the tether, from the base to the counterweight, using a constellation of surveillance satellites to watch for any object on an intercept course. How do we design a system that is both secure and open for business? The tether itself could be woven with fiber optic sensors that act like a distributed nervous system, capable of detecting the unique vibrational signature of an unauthorized climber or even the minute stresses of a tampering attempt. Any anomalous contact would trigger an immediate localized investigation by a security robot, while the affected section could be temporarily isolated from the main power and control grid. This intricate web of defenses highlights a delicate balance. We must build a fortress that does not feel like one, ensuring robust security without strangling the economic flow that justifies the elevator's existence. With this cosmic bridge secured, its true potential begins to unfold, not just as a transportation marvel, but as the central pillar for an entirely new space-based economy. That slender ribbon becomes the central artery for an industrial revolution, one that unfolds not on the factory floor, but in the pristine quiet of high orbit. The elevator's promise of cheap, routine transport unlocks a new economic paradigm, orbital manufacturing. By delivering raw materials and machinery to factories stationed in geostationary orbit, we can leverage the unique properties of space itself. The most profound of these is microgravity, a near-weightless environment where the forces that hinder production on Earth simply vanish. Here, metals can be mixed in perfect alloys without separating, and delicate protein crystals can grow to unprecedented sizes and purity, offering new pathways for life-saving drug development. The company Made in Space provided a crucial proof of concept. operating the first 3D printer aboard the International Space Station, demonstrating that complex tools and components could be fabricated on demand far from Earth. Manufacturing visionaries like Dr. Jason Dunn foresee this scaling up dramatically. Elevator-served orbital parks could host vast facilities for assembling next-generation telescopes with mirrors the size of football fields, constructing rotating space habitats with materials sourced from the Moon, and building the interplanetary ships destined for Mars, all without the constraints and vibrations of a rocket launch. One of the most immediate opportunities lies in producing ultra-pure semiconductors. On Earth, imperfections caused by gravity during the cooling process limit the performance of computer chips. In the stillness of orbit, these crystals can form flawlessly, potentially unleashing a new era of computing power. An illustrative case is the fabrication of entire satellite constellations in orbit. Freed from the need to survive a violent launch and fit inside a cramped rocket fairing, engineers can design satellites that are larger, more delicate, and far more powerful. They could be built as single, expansive units, with enormous antennas and solar panels that unfurl naturally, rather than deploying through a complex and risky series of hinges and springs. This shift from launching to building in space redefines the entire industry. What new professions might emerge in this orbital economy? We could see the rise of zero-gravity quality control specialists, monitoring production lines where fluids behave as floating spheres, and orbital factory managers who coordinate the flow of asteroidal metals and finished goods across a supply chain that spans the inner solar system. This burgeoning industrial capacity creates a powerful, self-reinforcing cycle. The very products of these orbital factories, from perfect ball bearings to advanced pharmaceuticals, would be shipped back down the elevator, generating immense value and fueling further expansion. This economic engine naturally extends its reach to tap the ultimate resource frontier, the mineral-rich bodies of the asteroid belt. This cosmic conveyor belt extends its reach to the untapped vaults of the solar system. The space elevator becomes the essential supply line for asteroid mining, ferrying rugged robotic prospectors out to near-Earth objects and guiding the return of their precious harvest. This synergy transforms the elevator from a mere transport conduit into the foundational enabler of true resource independence for our entire species. Early pioneers like the venture's planetary resources and deep space industries laid the conceptual groundwork, developing the core technologies for identifying and processing extraterrestrial materials. The economic incentive is staggering. Resource economists like Dr. Martin Elvis calculate that a single metallic asteroid, just a kilometer wide, could contain platinum group metals and rare earth elements with a market value measured in trillions of dollars. The elevator's revolutionary contribution is making the retrieval of these riches feasible, slashing the astronomical cost of repeated round trips to and from the deep gravity well of Earth. The detailed logistics form a complex interplanetary supply chain. One approach involves refining the raw ore right at the asteroid itself, using solar furnaces to melt and separate the valuable metals from the rocky slag. Alternatively, raw chunks of asteroid could be transported to dedicated orbital processing stations located near the elevator's counterweight. There, in the steady microgravity, industrial refineries would extract every ounce of value. The resulting pure metals or even pre-manufactured components would then be loaded onto descending climbers for their gentle ride down to waiting markets. This entire process demands rigorous safety protocols. Inbound climbers carrying extraterrestrial material would be subject to strict planetary protection measures, likely being quarantined and inspected at a high-altitude station to ensure no potential biological or chemical contaminants ever reach Earth's biosphere. There is also the economic consideration of how to introduce such a vast new supply of precious metals without causing disruptive shocks to global markets. A carefully managed, gradual release would be essential. Perhaps the most immediately valuable resource isn't a metal at all. Many asteroids are rich in water ice. This water is the oil of the solar system. It can be split through electrolysis into hydrogen and oxygen, the fundamental components of rocket fuel. The elevator would enable the construction of sprawling fuel depots in orbit, turning the Counterweight station into the ultimate cosmic gas station, servicing satellites, space tugs, and missions headed to the Moon and Mars. How might an influx of space-based platinum and water alter global economies and reduce the severe environmental impact of terrestrial mining? This vision of abundance hinges on the elevator's ability to function not for years, but for decades, a permanence that demands we consider its own long-term evolution and the upgrades required to maintain its cosmic relevance. A single elevator is a marvel, but a network would be a revolution. This is the natural evolution, the point where a solitary bridge becomes a sprawling interstellar port. Picture not one, but several of these slender ribbons, strategically placed around the equator, each one optimized for a specific purpose. One might be dedicated to hauling raw materials from asteroid mines, its design built for brute strength and durability. Another, constructed later with more refined technology, could be a passenger terminal featuring faster, pressurized climbers with panoramic windows for the ultimate sightseeing journey. These individual strands would not exist in isolation. They would connect to an orbital ring, a colossal structure encircling the planet, acting as a central hub where cargo and passengers are transferred to spacecraft bound for the Moon, Mars, or beyond. This creates a comprehensive logistics grid for the solar system, a highway in the sky. This pattern of growth mirrors the history of our terrestrial networks. The first transcontinental railway did not remain a single track for long. It spawned branches, feeder lines, and eventually an entire system that reshaped continents. Futurists like Dr. Isaac Arthur project that by the year 2100, such a multi-elevator system could be the backbone of a spacefaring civilization. The upgrades would be continuous. As new materials are discovered in labs, the original carbon nanotube tethers could be carefully replaced with even stronger ones, perhaps woven from boron nitride or theoretical materials we have not yet named. The tether itself might evolve into a dynamic structure, one that can subtly adjust its length to optimize for different solar cycles or to avoid accumulating debris. We could see climber lanes added for higher throughput, much like adding more traffic lanes to a busy freeway. Some concepts even propose modular counterweights, massive hubs that can be reconfigured or expanded to serve as shipyards, fuel depots, or even the foundations for rotating space habitats. How would society change if a trip to a lunar hotel or a research station on Mars became as routine as an intercontinental flight? The very concept of distance would transform, collapsing the scale of our solar system into something far more accessible. This inevitable expansion, however, forces a critical and responsible question. What is the environmental cost of building and operating such a massive planetary network? Every blueprint for a new world must be weighed on the scales of our old one. A full life-cycle environmental audit of the mega-space elevator forces us to confront a complex equation, balancing the undeniable impacts of its construction against the profound pollution it is designed to eliminate. This is not a simple comparison. We must quantify everything from the immense energy required to manufacture its advanced nanomaterials to the operational footprint of its base stations and power beams. Then stack that against the atmospheric cost of the thousands of rocket launches it would render obsolete. Environmental scientists like Dr. Kevin Noone highlight this crucial trade-off. The production of carbon nanotubes, for instance, could initially be a highly energy-intensive process, creating a significant carbon debt. Yet this upfront cost must be measured against a long-term future where the sooty exhaust plumes and black carbon deposits from conventional rockets, which can affect upper atmospheric chemistry, become a rarity. The elevator's clean, electric ascent promises a dramatic reduction in this specific form of atmospheric contamination, aligning with global sustainability goals. The assessment extends to the very ground we build on. A mobile ocean platform minimizes permanent land use, but the energy transmission sites require careful placement. The powerful laser or microwave beams used to propel the climbers must be sited in remote, secure locations, with their potential effects on local wildlife, particularly bird migrations, thoroughly studied and mitigated through advanced tracking and automatic beam shutdown systems. Even the end of the elevator's life is part of the plan. Decommissioning protocols would be designed from the very beginning, ensuring that the tether can be safely guided to a controlled re-entry over an empty stretch of ocean or even repurposed in orbit, leaving no trace of hazardous debris. This cradle-to-grave analysis reveals a powerful synergy. The same elevator that might have a complex initial footprint could become the essential conduit for truly transformative green technologies. By providing cheap, routine access to orbit, it enables the construction of vast space-based solar power stations, which beam clean, continuous energy back to Earth, potentially offsetting the project's entire carbon debt many times over. How do we ensure that this mega-project, conceived to carry us beyond our planet, does not inadvertently harm the delicate biosphere we call home? This rigorous ecological accounting is not just an engineering formality. It is the foundation of a broader ethical responsibility, a promise that our reach for the stars is guided by a commitment to preserve the world we leave behind. This slender ribbon suspended in the sky demands a new ethical framework, one that ensures it becomes a bridge for all humanity, not a private gateway for a privileged few. The core challenge is distributive justice, a principle championed by philosophers like Dr. James Schwartz, which asks how we can fairly share both the immense benefits and the profound responsibilities of this new frontier. Without deliberate international governance, we risk projecting our oldest terrestrial conflicts, our inequalities of wealth and power, directly into the cosmos. The most pressing ethical questions form a critical checklist for our collective conscience. How do we prevent this structure of peace from being weaponized, transforming a symbol of ascent into one of domination? How do we allocate climber slots and bandwidth so that a developing nation can launch its first satellite for the cost of a university education, ensuring its voice is heard in orbit? The process of choosing a base station location must involve deep consultation with indigenous communities, respecting their ancestral ties to the land and sea, turning a technical decision into a model of cooperative planning. A potential solution lies in creating a new international body, perhaps under the United Nations, modeled on the International Seabed Authority that governs the ocean floor. This authority could manage elevator operations, setting fair pricing and reserving capacity for scientific and humanitarian payloads. The revenue generated, which could grow to trillions of dollars over its lifetime, could be directed into a global trust fund, financing universal education, eradicating neglected diseases, and building climate resilience in the most vulnerable nations. This transforms the elevator from a piece of infrastructure into a perpetual engine for human development. How do we design a system where success is measured not in profit alone, but in the elevation of human potential everywhere? Weaving this strong ethical thread into the very fabric of the elevator's governance is the final, essential step in its construction, ensuring that when we finally step onto this cosmic bridge, we carry our highest ideals with us into the stars. This cosmic bridge becomes the ultimate springboard, launching us toward worlds once confined to telescopes and dreams. The space elevator's true power lies not in reaching orbit, but in what we do once we are there. It fundamentally redefines the economics of deep space travel. Instead of building a massive, fragile ship on the ground and launching it with a violent, fuel-guzzling explosion, we can construct our interplanetary vessels in the calm of space. Imagine a shipyard in high orbit, where components delivered by the elevator are assembled into a vessel designed solely for the vacuum, without the need for heavy heat shields or aerodynamic shapes. A ship departing from this orbital dock has already escaped Earth's deepest gravity well, requiring a fraction of the fuel to set course for Mars or the asteroid belt. This is the vision that transforms the elevator from a destination into a departure gate. Futurist Dr. Michio Kaku extends this logic, suggesting that a similar principle could one day apply to the Moon. A lunar space elevator, anchored to the Moon's surface and extending to a Lagrange point, would provide a low-energy route to transport materials mined from the lunar soil back to Earth orbit. This creates an integrated transportation network, a celestial supply chain where raw materials from the Moon are delivered to orbital factories via these elegant threads. The elevator's role expands further, serving as the deployment platform for the most ambitious journeys of all. Solar sails, vast and delicate sheets thinner than a soap bubble, could be unfurled at the Counterweight station. From that lofty perch free of atmospheric drag, they could catch the gentle but constant push of sunlight, accelerating probes to incredible speeds for interstellar missions. Magnetic sails could harness the solar wind itself, creating a propellantless drive system for robotic scouts headed to the outer planets. Perhaps the most profound application is the construction of generation ships. These would be self-contained worlds, built in orbit from materials steadily supplied by the elevator. They would be rotating habitats, using centrifugal force to simulate gravity, allowing generations of pioneers to live and work comfortably on a centuries-long voyage to a nearby star. What does it mean for our culture when the night sky is no longer a distant tapestry, but a neighborhood we are actively building and exploring? This shift from looking to traveling, from dreaming to departing, represents a philosophical evolution as significant as any technological breakthrough. This grand vision rests entirely on solving the final, practical puzzles that stand between our current reality and this stellar future. This grand synthesis of disciplines demands a new kind of engineering language, one spoken fluently by material scientists, orbital dynamicists, and artificial intelligence architects. Their collaboration moves beyond isolated solutions to create a single, resilient, and adaptive organism. The choice of a tether material is no longer just about tensile strength. It directly dictates how the entire structure will sway. A stiffer composite might resist certain oscillations, while a more flexible one could require a more sophisticated AI damping system to control its motion. Similarly, the design of the ground-based power beam does not merely push climbers upward. It influences their safe speed and the thermal management needed to prevent overheating during the long ascent. This is the realm of systems engineering where visionaries like Dr. Donna Shirley advocate for a holistic approach. They propose building a complete digital twin, a virtual replica of the entire elevator system that lives inside a supercomputer. This digital twin allows engineers to run countless simulations, watching how a new maintenance robot design might affect the tether's harmonic balance, or how a software update for the climbers could inadvertently create a traffic jam 50,000 kilometers high. Key integration points become critical puzzles. The design of the robotic inspectors must be perfectly aligned with the radiation shielding strategy, ensuring their electronics can survive long-term exposure while performing delicate repairs. Cybersecurity protocols essential for protecting the command network must be woven in so seamlessly that they do not introduce a fatal delay in an emergency thruster firing. A single breakthrough in one field can send ripples of innovation across the entire project. The discovery of a practical room temperature superconductor, for instance, would not only enable frictionless magnetic levitation for the climbers, but could also revolutionize how energy is stored and transferred along the tether's length, solving two monumental challenges with one elegant principle. How do we cultivate these cross-disciplinary teams, where an AI programmer understands the material science constraints and an orbital mechanic thinks in terms of network security? The answer may lie in shared virtual workspaces, where experts from every corner of the globe can collaborate inside the digital twin, seeing the immediate, system-wide impact of their design choices. This intricate technical weave connecting every strand of the project finds its real-world beginning not in orbit, but in the focused, determined efforts of research labs and startup garages today. The dream is no longer confined to sketches on a whiteboard. In laboratories from Tokyo to Munich, researchers are wrestling with the physical reality of the space elevator, grappling with microscopic samples that must one day form a cable to the stars. The Japanese construction giant Obayashi Corporation has publicly committed to building an operational elevator by the year 2050, a vision that begins with humble, small-scale demonstrations, like robotic climbers ascending a short tether in a vacuum chamber. This long-term ambition is mirrored by a global, decentralized research effort. Universities, government space agencies, and nimble private firms are all contributing pieces to this colossal puzzle. Their collaboration is formalized at events like the annual Space Elevator Conference, where experts from every discipline gather to share data, debate failures, and celebrate incremental victories. Dr. Peter Swan, president of the International Space Elevator Consortium, reports that laboratory tether samples have already surpassed 50% of the required specific strength for a full-scale elevator. This is not a theoretical number. It represents a tangible material milestone on the path to feasibility. Concrete initiatives are providing crucial testing grounds. NASA Centennial Challenges have historically spurred innovation by offering prizes for breakthroughs in beamed power and tether robotics. Across the Atlantic, the European Space Agency is conducting detailed studies on how to protect a permanent tether from the ever-growing cloud of orbital debris. One of the most exciting near-term projects is the Star-C initiative. Its plan is to deploy a mini-tether just a few kilometers long from the International Space Station. This experiment would provide the first real-world data on how a flexible tether behaves in microgravity, how it responds to thruster firings, and how its materials withstand the harsh space environment. This groundswell of activity raises a compelling question for anyone inspired by this vision. What can everyday citizens do to support these foundational efforts? Public engagement is a powerful catalyst. You can follow the research, discuss the challenges in online forums, and support educational outreach that inspires the next generation of engineers. This grassroots momentum, built from countless small contributions, is what will ultimately help clear the immense regulatory and diplomatic hurdles that lie ahead. This legal framework is a new frontier in itself, a complex web of treaties and technical standards that must be woven before the first strand of the tether is ever launched. Unlike a ship or an aircraft, the space elevator defies simple classification. Is it a spacecraft subject to launch and re-entry protocols, or is it permanent infrastructure akin to a transoceanic cable or an international bridge? Legal scholars such as Dr. Stephen Freeland emphasize that this question of legal status is the first major hurdle, as it dictates which set of existing laws, if any, will apply. The issue of jurisdiction creates a vertical challenge. A climber ascending from a sea platform in international waters passes through sovereign airspace before reaching the freedom of outer space. Which nation's laws govern an incident that occurs at an altitude of 50 kilometers, and how does that authority shift as the vehicle climbs higher? This ambiguity demands new agreements that clearly define responsibility along the entire length of the structure. Safety standards will form the bedrock of this new regulatory body. These would cover every component, from the mandatory fail-safe systems on every robotic climber to the rigorous testing of the tether's material for long-term fatigue. Environmental impact assessments would be required not only for the ocean-based station, but also for the effects of the power beams on the upper atmosphere and the potential risks of any material re-entering from high altitude. The process for resolving disputes between operator nations must be established in advance. If a climber from one country's segment causes damage to the tether owned by another, a pre-agreed arbitration framework would be essential to prevent international conflicts from stalling the entire enterprise. A potential model for this global cooperation already exists in the International Civil Aviation Organization, which harmonizes the rules for air travel across borders. A future international space elevator organization could play a similar role, setting universal safety and operational protocols while managing the precious orbital slots the elevator would occupy. How can we design these regulations to be strong enough to ensure safety and security, yet flexible enough to accommodate the rapid technological innovation that will inevitably follow? Establishing this clear and fair legal pathway is not a bureaucratic afterthought. It is the essential foundation that will give nations and private investors the confidence to commit the trillions of dollars and decades of effort required. That slender ribbon becomes a shared promise, a project too vast for any single nation to shoulder alone. Its construction would likely follow a 24th partnership model, a global alliance echoing the cooperative spirit that built the International Space Station. This is not a simple handshake deal, but a deeply integrated consortium of nations pooling their financial resources, technical expertise, and political risk. The core logic is one of comparative advantage. One country might contribute its unparalleled material science research on carbon nanotubes, while another provides the heavy lift launch capacity for the initial seed tether. A third partner could specialize in the sophisticated artificial intelligence required for tether stability and traffic management. Partnership governance expert Dr. Scott Pace from the George Washington University Space Policy Institute observes that trust building through joint projects, such as a lunar base, creates the essential diplomatic capital needed for a venture of this magnitude. The framework for this collaboration would be a complex web of memoranda of understanding, meticulously outlining each nation's role, its financial commitments, and its share in the long-term profits generated by the operational elevator. This raises intricate questions of intellectual property. Who owns the patents for the revolutionary technologies developed during the construction process, and how are those licensing rights shared among the partners? The alliance must also establish clear conflict resolution mechanisms, pre-agreed arbitration panels to settle disputes without resorting to political brinkmanship that could halt construction for years. A pivotal consideration is inclusivity, creating pathways for emerging spacefaring nations to join the consortium, ensuring the elevator does not become the exclusive domain of a few established powers. Consider the potential of a United States, China, and European Union alliance. Despite current geopolitical tensions, the transformative nature of this project could provide a powerful incentive to find common ground. Such a trio would combine immense manufacturing capacity, advanced robotics, and deep space experience. What confidence-building measures could convince rival states to collaborate on such a strategic asset? The answer may lie in transparent, phased contributions and mutual interdependence, where no single partner can control or complete the system without the others. With such alliances solidifying, we can begin to project a realistic timeline from a shared concept to a functioning reality, charting the decades-long journey of turning this global dream into steel and carbon in the sky. This grand project spans a full century, a patient roadmap of human ingenuity. The journey begins in the 2030s with the foundational leap, achieving material breakthroughs that produce the first continuous, macro-scale ribbons of carbon nanotubes with the necessary specific strength. The 2040s would then see the initial deployment, launching a slender seed tether and its counterweight to geostationary orbit, a fragile thread cast into the celestial void. By the 2050s, the first robotic climbers would begin their slow, cautious ascent in testing chambers and along prototype tethers, proving the core mechanics of beamed power and traction. Full-scale cargo operations could become a reality by the 2070s, with the first routine shipments of satellites and construction materials gliding silently upward. Passenger service, the ultimate culmination, might finally arrive by the year 2100. This phased timeline, synthesized from forecasts by groups like the International Association of Advanced Materials, deliberately accounts for the inevitable setbacks in funding and the slow, iterative nature of technological maturation. Timeline analyst Dr. David Smitherman stresses that public engagement and unwavering, long-term investment are the true fuel for this marathon, preventing the dream from stalling in the decades between major milestones. The path is marked by critical achievements, such as fabricating that initial, flawless nanotube ribbon of sufficient length, demonstrating a climber's complete function in a simulated space environment, and most critically, securing the complex international regulatory approvals that grant the project its legal right to exist. The Obayashi Corporation's ambitious roadmap, targeting a 100,000-ton capacity elevator by 2050, represents an optimistic projection, one wholly dependent on advances we have not yet proven in any laboratory. This extended horizon prompts a compelling question. Could a sudden, disruptive leap in a parallel field, such as artificial intelligence for system management or quantum computing for material simulation, dramatically accelerate one of these phases, collapsing a 20-year development cycle into just 5? As we near the conclusion of this exploration, the sheer scale of the timeline forces a moment of profound reflection. Succeeding in this endeavor would mark a permanent transition for our species, establishing a secure and sustainable foothold in the solar system. Failing, however, would represent more than a technical setback. It would be a collective choice to remain confined, a decision to accept the immense cost and environmental impact of rocketry as a permanent limit on our future. The true legacy of the space elevator is not merely the structure itself, but the generations of perseverance and global cooperation it would demand, a testament to whether we can look beyond our own lifetimes to build a bridge for all of humanity. Success would echo far beyond the launch pad, fundamentally reshaping our civilization from the ground up. We stand at the precipice of a post-scarcity era, where the material limitations that have defined human history begin to dissolve. Orbital manufacturing and the influx of resources from asteroid mining could render many traditional constraints obsolete. Economists like Dr. Robin Hanson suggest that global economic growth could enter a period of unprecedented expansion as space commerce unlocks entirely new sectors and revenue streams. This is not merely an economic shift, but a societal transformation on the scale of the Industrial Revolution, elevating global living standards and redefining the very nature of work. Millions of new professions would emerge, from zero-gravity horticulturalists to orbital habitat architects, creating a job market that spans two worlds. This new abundance would manifest in our daily lives in tangible ways. The cost of electronics could plummet as rare metals from asteroids become commonplace, democratizing access to advanced technology across the globe. The decentralization of manufacturing would continue, with orbital factories producing perfect goods that are shipped down the elevator, while Earth-based industry focuses on sustainable, localized production. Energy crises could become a relic of the past thanks to vast solar power stations built in orbit, beaming clean, continuous electricity to the planet. This cascade of plenty would inevitably influence our culture, giving rise to new art forms and architectural styles inspired by the sublime vistas of space and the engineering marvels of orbital life. With this expansion comes a profound philosophical evolution, as space-based medical research in microgravity leads to breakthroughs in tissue regeneration and drug development. Human health spans could extend significantly. This potential decline in mortality rates invites deep ethical consideration about the structure of society and the meaning of a fulfilling life across extended years. Our very identity would transform to include off-world citizenship, fostering a new perspective where national borders feel less significant than our shared status as a spacefaring species. Space tourism would evolve from a luxury for the few to a mass-market experience, allowing ordinary people to gaze upon the curvature of Earth, an experience that often sparks a lasting sense of planetary stewardship and unity. Such radical change is not without its dislocations. Terrestrial industries like traditional mining and launch services would face immense disruption, requiring global strategies for workforce retraining and economic transition. The management of this new wealth demands careful thought to ensure it reduces inequality rather than exacerbating it. How do we structure an economy where the core drivers of value are no longer scarce? The answers will challenge our deepest assumptions about economics, governance, and our place in the cosmos. This bright future, brimming with possibility, is the ultimate prize. But claiming it requires us to first consolidate every lesson learned and confront the final, summary challenges that stand between our current reality and this stellar destiny. This journey through the mega-space elevator reveals not just a machine, but a mirror of our own ambition. We have confronted the search for a perfect material, the fury of our atmosphere, and the silent music of orbital physics. We have weighed the immense costs against the promise of a new economy and grappled with the need for global cooperation to protect this shared bridge. Each of these hurdles underscores a single, profound truth. This is not merely about building a more efficient rocket. It is about forging a permanent, sustainable pathway off our planet, one that redefines access to orbit as safe, affordable, and as routine as a transoceanic flight. The visionary author Arthur C. Clarke once offered a guiding light for such endeavors. He said, "The only way of discovering the limits of the possible is to venture a little way past them into the impossible." Our exploration of the space elevator is precisely that kind of venture. It stretches our imagination and tests our resolve, pushing the boundaries of what we believe we can achieve. Now we turn this conversation over to you. After this deep dive, which challenge strikes you as the most daunting to overcome? Is it the creation of that flawless carbon nanotube ribbon, or perhaps the intricate global diplomacy required to govern it? And on the other side of that effort, which potential benefit ignites your excitement the most? Is it the dawn of orbital manufacturing, the promise of asteroid mining, or the simple idea of looking down at Earth from a climber's window? Share your perspective in the comments below. Your voice is part of the collective momentum that will one day turn such dreams into reality. If you found this journey inspiring, subscribe for more deep dives into the futuristic technology that is actively shaping our tomorrow. Let us continue this conversation about building a legacy among the stars, because the future is not a place we are going, but one we are building together.